Hi guys, welcome back to YouTube channel Chemistry Lab UGPG. So today we are going to talk about alcohols, phenols, ethers and epoxides. This is 6th paper, Unit 2, Lecture 4. So this will be highly useful for BSc Chemistry students under CBCS syllabus. So I have a simple message for you guys. Please think for innovation, be creative, learn everywhere, anytime and help to learn others. So today we are going to talk about phenols, preparation, properties, acidity and factors affecting it and ring substitution reactions. So this is the general formula of alcohol ROH. So now if we substitute this R group with a AR group or phenyl group, so that becomes C6H5OH. So that is called phenol and it is aromatic in nature. So this phenol, that is the enol form. So now it can tautomerize to give rise to less stable form, that is the keto form. So here the phenol, it is more stable because this is resonance stabilized. So similarly in acetone, so the keto form is more stable and when it tautomerizes, it gives rise to enol. Okay, so here the delta H for this reaction is plus 58.5 kilojoule per mole. So this enol form is less stable. Now question arises why the phenols are important. So it is used for synthesis of dyes, phthalate dyes, drugs like aspirin, polymers like bakelite. So here are some compounds, the 1,2-dihydroxy phenol. So that is called catechol. When this OH groups at 1,3 position, that is called resorcinol. 1,4 position, that is quinol. And this is the structure of a benzyl alcohol. Next is preparation of alcohol. So we can start from sulfonic acids. So sodium paratoluene sulfonate. So you can treat with sodium hydroxide. So you can end up with sodium phenoxide. And for the treatment with sulfuric acid, you can get phenol. Similarly, we can prepare from diazonium salt. So this is the diazonium salt. We can treat with water and H+. You can get the phenol. Similarly, hydrolysis of aryl halides. So this nitro substitute, the nitro derivative of this aryl halide can be treated with sodium hydroxide and further treatment with H+. So you can get 2,4-dinitrophenol. Similarly, commercial method from cumene hydroperoxide. So this is the compound called cumene, and upon reaction with oxygen, you get this cumene hydroperoxide, and upon treatment with sulfuric acid, you get phenol. So this cumene hydroperoxide, so oxygen lone pair will attack to H+, so you get this OH2+. So again here, this bond will migrate to oxygen and it will kick out to water. So you end up with this carbocation. So again water will attack to this carbocation. So you get OH2+. So loss of proton. So here this bond move like this and see this CO bond will break on oxygen. So you get this phenol. Similarly, another method is Dawes process. So chlorobenzene is treated with 10% sodium hydroxide at 350 degrees Celsius and 200 atmosphere. So you get sodium phenoxide, and upon treatment with acid you get phenol. And another method is called Raschig process. So chlorobenzene is treated with sodium hydroxide, cuprous chloride or ferric chloride at 250 degrees Celsius. So you get sodium phenoxide, and upon treatment with steam 425 degrees Celsius and pressure, you get this phenol. Similarly, benzene can be oxidized in presence of oxygen and vanadium pentoxide. You get this phenol. The next is the properties of phenols. So pure phenols are colorless liquids or solids, but they can turn reddish due to atmospheric oxidation. Phenols are generally insoluble in water. Phenols have high boiling points due to intermolecular hydrogen bonding. Orthonitrophenol has lower boiling point and less solubility in water. than meta and para isomer due to intramolecular hydrogen bonding. Substituents like nitro group impart yellow color to phenols. The next is acidity of phenols. So phenols are fairly acidic compounds which form salts, phenoxides, on reaction with alkali metal hydroxides. So phenol upon reaction with sodium hydroxide, you get phenoxides. So it is soluble in water, insoluble in organic solvent. So phenols do not react with carbonates or bicarbonates. So phenol pK has 8.9, carboxylic acid pK 5, alcohol 16 to 18, and carbonic acid 7. So hence phenols are much more acidic than alcohols, but less than carboxylic acids or even carbonic acid. So if we compare phenol with alcohol, so ROH react with OH minus ion, so you get RO minus. And phenol again react with OH minus ion, so you get phenoxide anion. So alkoxide ion is a single structure, whereas phenol or phenoxide ions are resonance stabilized. So the equilibrium towards ionization of phenol is favored relative to ionization of alcohol. Hence Ka for phenol is higher than alcohol. So if we compare phenol with carboxylic acid, so here RCOH will ionize to give rise to RCO minus plus H plus, and this carboxylate anion is resonance stabilized. So the hybrid of a carboxylate ion is relatively more stable than phenoxide ion. So the hybrid structure, resonance hybrid structure, is more stable than phenoxide ion. So a carboxylic acid is more acidic than phenol, so have lower pK than that of phenol. So if we compare phenol with carbonic acid, so this is the carbonic acid H2CO3, so it gives this HCO3 minus plus H plus. So it is resonance stabilized and it can have equivalent contributing structures like this. So the equivalent contributing structures of carbonic acid makes it fairly strong acid which phenol lacks, and hence carbonic acid is a stronger acid than phenol. So electron withdrawing substance like nitro group or chlorine etc. enhance the acidity, but electron releasing substituents like alkali groups will decrease the acidity. Next is effect of substituents on acidity of phenol. So if we have nitro group, electron withdrawing groups like nitro group in ortho or para position, it would stabilize the phenoxide ion by dispersal of a negative charge through resonance effect. So through these resonating structures, so the negative charge on oxygen will be dispersed and it will stabilize the phenoxide ion. So hence electron withdrawing groups like a chlorine group would also stabilize the phenoxide ion by charge dispersal through powerful electron withdrawing inductive effect. Hence electron withdrawing groups in a phenol would stabilize the phenoxide ion and hence acid strengthening, so which is evident from low pKa values. So here you can see phenol 8.9, orthonitrophenol 7.2 lower pKa, paranitro 7.1, metanitro it has higher 8.3, 2,4,6 trinitrophenol 1, then orthochlorophenol 8.1, parachlorophenol 8.6, metachlorophenol 8.4. So similarly electron withdrawing groups, electron donating groups like alkali groups would destabilize the phenoxide ion by intensifying negative charge through electron releasing inductive effect or resonance effect. So electron donating groups will decrease the acidity of phenol. So here orthocresol 9.2, metacresol 9.0, paracresol 9.2 and phenol 8.9. So next is ring substitution reactions of phenol. So first reaction is halogenation. So phenol can react with bromine water, so giving rise to tribromo derivative. Similarly, it can undergo nitration with dilute nitric acid. You can have ortho and paranitrophenol, and upon treatment with concentrated nitric acid, you can have picric acid, trinitrophenol. Similarly, it can undergo reaction with sulfuric acid. So sulfonation. Similarly, diamond reaction. It can undergo reaction with CaCl3 and sodium hydroxide. So salicylaldehyde. Kloof-Smith reaction. Sodium hydroxide and carbon dioxide. You can have salicylic acid. Similarly, it can undergo Friedel-Claps acylation and alkylation. Similarly, it can undergo Elb's persulfate oxidation. So phenol can react with K2S2O8, giving rise to quinol. So here is the phthalate reaction. So phenol can react with phthalic anhydride. So you can have phenolphthalein. So here it has pH 9.9 to 10, and in basic medium it gives pink color. So by reaction with sodium hydroxide, you can have this quinoid structure which impact pink red color. Similarly, this phenol or phenoxide ion can react with bromine, and ultimately it gives rise to tribromophenol. Similarly, phenoxide can react with K2S2O8, giving rise to this quinol. So here is the mechanism. So here O minus come here, this pi bond will come here, and this pi bond will attack to this oxygen, and it will kick out KSO4 minus. So again loss of proton, again it will destabilize, it will revive the aromaticity. So you can have this oxyanion. So upon treatment with H3O plus, we can have quinol. So please subscribe to our channel Chemistry Live UGPG. So this is also available in the website www.chemistryliveugpg.com. Class 11th and 12th student, this is the channel Foundation Chemistry AV. So this is a simple step towards e-learning, making life better. Thank you for learning.